Rocket propulsion first began to take shape over 800 years ago with the invention of Chinese solid propellant rockets named fire arrows to repel Mongol invaders. Today, rockets have advanced to immense heights, but the overall design of liquid bipropellant engines has not really changed since the space race. However, a new form of propulsion has begun to take shape in the past couple of decades, which uses a novel form of propulsion called detonation. Using the physics of supersonic combustion, these engines have the potential to increase the efficiency of rocket propulsion by up to 25%. We are Team 25038, and this is our liquid propellant rotating detonation rocket engine.
Our sponsors, Nobel Works and R3 Aerospace, have tasked us with creating a bipropellant rotating detonation rocket engine, also known as an RDRE. These engines are ignited by the use of a deflagration to detonation tube, also known as a DDT tube. This tube generates a sonic flame front that accelerates and enters the combustion chamber tangentially, allowing the fuel to be ignited and thus propagate in an annular direction.
The goal of this project is to design, manufacture, and test a liquid RDRE. The engine uses liquid oxygen or LOX as an oxidizer and a proprietary blend of ethanol known as RPX, synthesized by our sponsor, as the fuel. The engine is designed to operate at a chamber pressure around 250 psi. Our design consists of three systems: the RDRE, the fuel and oxidizer management systems, and the data acquisition system.
The fuel and oxidizer management system is mounted on R3 Aerospace's static fire stand and uses most of its original components. There are two storage tanks to hold the LOX and RPX. These tanks both have fill valves which pressurize the system, as well as venting valves for safety. There are also the two main pneumatic valves used for starting the engine. Feed tubes from the tanks connect to a manifold, which then splits into several 1/8-inch stainless steel pipes. These pipes connect directly into the injector plate via 1/8-inch MBT swage locks. The DDT tube is fed propane and oxygen before firing the engine. Once the body is filled, the solenoids will close and the spark plug ignites the small propellant mixture right before the injector plate begins atomizing the main propellant. This is how the engine is ignited.
The design of the engine was made around an existing combustion chamber from the previous year's senior design project. The engine consists of 6 major components: the injector plate, the outer combustion wall, the inner combustion plug, the aerospike nozzle, the aerospike shroud, and the nozzle spacer plates. The injector plate consists of 45 triplet sets. Each triplet consists of 2 fuel and 1 oxidizer orifice. The fuel orifice have an angle of 6 degrees between them, called the impingement angle. These were designed around previous research and testing from other RDRE groups, such as NASA. In order to feed each of the respective propellants, we decided to go with a triple feed channel design. Each channel is fed propellant by 4 equally spaced swage locks.
Here are some 3D printed models of our parts that we use to test how they fit together. We have the injector plate here, and here is the inner chamber wall, or plug as it's called. It seals to the injector plate using an O-ring, like so. And then at the top it contours out to meet the outer diameter of the aerospike. We chose an aerospike because it's efficient and easy to install, and it allows our engine to produce the thrust that we want it to. We then used an already manufactured outer chamber wall that also seals to the injector plate with an O-ring, like so. And then on top of the outer chamber wall, we put a shroud. This shroud forms the outer side of the nozzle that the combustion products flow through as they leave the engine.
During testing, we wanted to resolve the detonation wave inside the combustion chamber, as well as sample the chamber pressure and thrust produced. For this, we used a MicroStar DAP 5400A high-speed data acquisition card, which was supplied by our sponsor. This card can sample up to 2 MHz of analog input. We used 2 PCB ICB pressure transducers to resolve the detonation wave. We used a single Omega 1000 PSI IC pressure transducer to measure the chamber pressure during a static fire. And we also used a 200 kilogram load cell to measure the thrust produced.
Testing was the moment we've been building towards since day one, where design meant reality. We started with our MVP 1B, which was the single triplet injector. This was used to validate our feasibility for the full injector plate before moving on to manufacturing of the full plate. To simulate flow, we used the water test. The spray cone formed was shown even distribution as well as proper atomization, which told us that our initial triplet injector design was feasible.
From there, we built the full engine, a 3D printed aluminum injector plate with 45-degree triplet injectors, a stainless steel combustion chamber, and our custom aerospec nozzle. After full assembly, we conducted a series of pressure tests, taking the line pressures up to 300 psia.
We encountered some issues during manufacturing, but we developed a quick and effective solution to help us complete our engine build and stick to our timeline. The next step was to run a mass flow rate test on the whole injector plate. This was conducted at R3 Aerospace using water as our medium to test both atomization as well as mass flow. This test was successful and verified the mass flow rates for our fuel holes. Once this test was completed, we oxygen cleaned the rest of the components that would be coming in contact with the liquid oxygen during operation. This was critical for our safety and structural integrity because any hydrocarbons that come in contact with liquid oxygen will most likely combust due to the highly volatile nature of liquid oxygen. At R2, we set up a high-speed pressure transducer to track the velocity of our detonation wave, as well as a calibrated load cell to measure thrust. Our goal is to demonstrate a sustained detonation wave, as well as over 200 force-pounds of thrust. Unfortunately, during our static fire, it was not successful. We encountered issues with our ignition system as well as our data acquisition system. At the time of submission, we have fixed all of our issues and are currently working on a test date with our sponsor. We are confident that our engine will meet all performance requirements during this next phase of static fire testing.
No rocket engine project is complete without a few challenges. Our injector design originally was based off a Tesla valve, which was compact, efficient, and it prevented backflow through its geometry directly. However, when we looked into 3D printing this injector, we realized that it wasn't going to be possible. So instead, we pivoted our approach to a typical rocket injector design, which was a triplet straight injector. And after 3D printing, we still experienced fusing of these holes, so we had to go and work with Argus Machine here in Tucson to redrill these holes manually.
When working with high-pressure liquid oxygen and fuel, safety isn't optional. We followed safety protocols from both R3 Aerospace and NobleWorks. That included wearing full eye and ear protection, following safe distance procedures, and having constant supervision by experienced personnel. Every test we performed was pre-checked and controlled.
We had built and assembled every subsystems, pressure tested, and prepared for a full detonation capable static fire. We are proud of what we have accomplished, and we believe these systems will meet the performance targets we set out to achieve.
This project was a massive undertaking and one of the most valuable experiences of our academic careers. From concept to combustion, we've applied everything learned in the classroom and pushed beyond it. We thank NobleWorks and R3 Aerospace for trusting us with this challenge, and for their guidance, resources, and collaboration throughout the year. We also want to thank our mentor for their support and feedback, as well as acknowledge the previous research that contributed to our RDRE design. We're Team 25038, and we are proud to share our rotating detonation rocket engine with you at Design Day 2025. Thank you for watching.